second speaker this morning is Kerman, and he'll talk about Hofer's geometry, geodesic flows, and Maslov class rigidity.
Well, I would also like to thank the organizers for the invitation. I'm a bit worried for you that you're setting the bar too high for hosting duties, but as a participant, I'm happy to sit back and see how high you guys will go. So last time I had the pleasure to be here, I spoke about relationships between Hofer's geometry on the group of Hamiltonian diffeomorphisms and existence problems for periodic orbits. So in many ways, the topic of this talk will be an application of these ideas, although I'm not sure how clear I'll be able to make that point during the lecture. But the applications are to what's referred to as Maslov class rigidity. So let me describe that first. Okay, so the classical Maslov class is the following object. So let's let lambda n be the Lagrangian Grassmannian, so the set of Lagrangian subspaces of R2n. And the classical Maslov class is a homomorphism mu from the Lagrangian Grassmannian to Z. And here's one particularly simple description. Well, you can identify the Lagrangian Grassmannian with un over on. And we have a nice map on the space when we think of it in this way. We have the following map to S1. Well, this map, of course, exists on un. It doesn't descend to the quotient for obvious reasons. So we have to consider it square. Square descends to the quotient. And the Maslov class is defined, you can define it in terms of a degree. So if we have class gamma, sorry, this should be a homomorphism from pi 1 of the space. All right. So if we have a class in the fundamental group of the Lagrangian Grassmannian, we can consider, we can consider a representative. So that's a loop of Lagrangian subspaces. And then we can compose that with the square of the determinant map. And so this will be a map from S1 to S1. And then we can take the degree of this map. And that would be the value, of course, that's an integer, and that would be the value of the Maslov class on gamma. Okay, so one can see from this description that the Maslov class is some kind of winding number. If you take the case n equals 1, these are just lines in R2, and you can realize this is two times the winding number if you like. All right, using the classical Maslov class, one can describe very easily an invariant of Lagrangian submanifold up to Lagrangian isotopy. So let's let L be a Lagrangian submanifold of a symplectic manifold. And just using the classical Maslov class, we get a homomorphism from, in this case, the second relative homotopy group to Z, which is defined explicitly in terms of the classical Maslov class as follows. I guess I shouldn't write that line beside that line. So, of course, if we take a class in this relative homotopy group, it defines a trivialization of the tangent bundle of M along a loop in L. So this gives us a trivialization, let's say, of the tangent bundle to M along a loop. So we'll just identify that with R2n cross S1. Sitting inside that is, of course, the tangent space of L along that loop. Where here gamma is a loop on L. Okay. So inside here is TL restricted to gamma, and with this trivialization, we get a loop of Lagrangian subspaces in a symplectic vector space. And then we take the classical Maslov class of that, and that is, of course, an integer. And this is a homomorphism. Okay. Okay, so Maslov class rigidity. So this is obviously an easy to describe invariant, and it's come to play a prominent role in many aspects of symplectic topology. It arises in terms of index computations. But it's interesting in terms of being an invariant of a Lagrangian submanifold up to Lagrangian isotopy in itself. Now, Maslov class rigidity refers to restrictions on this homomorphism which one cannot see via homotopy theory. Okay? One needs to use so-called hard methods in symplectic topology, which essentially means that at some point you're going to have to consider a holomorphic curve equation. Okay, so this phenomenon of Maslov class rigidity was discovered essentially simultaneously by Viterbo and Polterovich in 89 or 90. Their results hold for Lagrangian submanifolds of symplectic vector spaces. So let me see. So let me state Viterbo's theorem, or a bit of a truncated version of Viterbo's theorem. I think 89 is probably right. So let L be a Lagrangian submanifold of even-dimensional Euclidean space with its standard symplectic structure. I haven't said it yet, but let me just say it once. All Lagrangians I consider would be compact without, so closed manifolds, compacting without boundary. So let's let L be a Lagrangian submanifold. Which admits a metric with non-positive sectional curvature. Okay, then we have the following conclusion. Before I state it, let me say that the restrictions on the Maslov class are in some sense a bit coarse. They can all be described in terms of one simple number, the minimal Maslov number. So let me jump aboard and define that. So of course we have a homomorphism from pi to ml. Actually, this is entirely similar to the minimal Chern number that Victor described in his talk. We just look at the image, which is a subgroup of the integers, and we take the smallest positive, well, we take the positive generator, non-negative generator, I guess. Okay, so if you can express a restriction in the minimal Maslov number, you're saying that the twisting of the tangent spaces along loops in L is at least this big. Okay? Okay. So the restriction here is that the minimal Maslov number of such a Lagrangian is between, well, for him, okay, is between 1 and n plus 1. So the minimal amount of twisting can't be too big. It's bounded by half the dimension plus 1. All right, so Viterbo's proof uses his proof of the Weinstein conjecture in R2n, and it really takes full advantage of the linear structure in the ambient space. He uses finite dimensional, so he considers a variational problem for Hamiltonian dynamical systems, which I'll describe in a second, uses finite dimensional reduction and equivariant homology. So most of these techniques are unavailable for more general ambient symplectic manifolds. However, one would, of course, like to have restrictions on the Maslov class for Lagrangians of more general symplectic manifolds. Here's the setting which it is reasonable to consider. Let's let L be a Lagrangian submanifold of a general symplectic manifold. But in order to get a meaningful setting to find rigidity results, you need to, it seems necessary to restrict yourself to displaceable Lagrangians. So let's let L be displaceable. Also a notion which has arisen in several talks. I'll just remind you, i.e. there exists a Hamiltonian diffeomorphism, or the time one map of a Hamiltonian flow, such that the image of L does not intersect L. Okay, so this assumption precludes several examples where the Maslov class is essentially trivial. So if you look at the zero section, a cotangent bundle, the domain of the Maslov class is trivial. So this precludes these examples. But it also is extremely important in even starting to establish rigidity results. So just as a simple example, every Lagrangian submanifold of a symplectic manifold of the form, let's say P cross R2, where P is another symplectic manifold, let's say with a symplectic form sigma plus a standard form in R2, as long as you have a factor like this, everything is displaceable. So there are some reasonably interesting examples where every Lagrangian is displaceable. Okay, so now how does one detect rigidity results, or in particular restrictions on the minimal Maslov number, while using holomorphic curves? I would like to describe a few general approaches to the problem, and then just focus on the one I used. All right. So the first approach I'd like to describe is to use Lagrangian disks, or sorry, holomorphic disks with boundary on Lagrangians. And this is the approach used by Polterovich. This is the method that he introduced. Although I won't describe it as Polterovich used it, I'll describe it as it's been used more recently in terms of Lagrangian floor homology. So you start with a displaceable Lagrangian submanifold, and, well, you want to draw some implications of this, and you need some assumptions. So the assumptions you need are that, in this approach, is that L is orientable. Also an assumption that is kind of tacit in Viterbo's work, but not explicitly stated. You need orientability, and more importantly, you need a monotonicity condition. Probably people can relax strict monotonicity, but I'll remind you that a Lagrangian submanifold is monotone if, you look at the class mu L. This takes integer values, and it's proportional to the symplectic structure when you restrict them to the relative homotopy group. Okay, so this is, if we change this to the Chern class of the symplectic manifold, and this to just pi 2 of m, this would be how you would define a monotone symplectic manifold. This is the definition of a monotone Lagrangian. This is, sorry, yeah? Is it okay to have 0 on both sides? Well, then the Maslov class would be trivial. Well, it's a good question. Whenever you...
I know it does not happen.
Okay, that's my answer. It does not happen. Whenever you're in this setting, you can prove rigidity results and prove that that's never 0. So you won't have displaceable Lagrangians. This precludes displaceable Lagrangians in that case. Does that make sense? Okay. In this case, well, one can draw some conclusions in terms of holomorphic disks. The shortest version of this would be that the Lagrangian floor homology of L with respect to, let's say, its image under the Hamiltonian diffeomorphism, which displaces it, is trivial. Okay? This is not an obvious fact. Well, it follows from the properties of Lagrangian, well, really the definition of Lagrangian floor homology. This is the homology of a complex which is generated by the intersection points of these two things. So if there are no intersection points, there's trivial homology. Now, one can draw conclusions on the Maslov class based on this equality for the following reason. The Maslov class is involved in the indexing of this homology. It controls the degrees of homology. So this is an observation due to O. This implies that the minimal Maslov number can't be too large. It has to be between 2 and n plus 1. And this is also not obvious. It involves what's known as O spectral sequence. But this is a first pass at what the argument looks like. So the second approach I wanted to describe involves Hamiltonian dynamical systems, which is more appropriate for the conference. And this approach is the one initiated by Viterbo. So one first takes advantage of the following well-known fact. If we have L inside of, well, any Lagrangian submanifold, we can find a neighborhood of that Lagrangian submanifold, which looks like a neighborhood in the cotangent bundle. So we can consider U as a neighborhood in the cotangent bundle of L. And within this neighborhood, we have a natural class of dynamical systems with which to work. We can fix a metric G on L. So let's fix G on L. And, well, so we can think of the cometric in T star L, and we can consider Hamiltonians of the form H. I will describe in a second. These will be supported inside of U. Okay? These Hamiltonians would be 0 outside of U, and inside of U we have kind of standard PQ coordinates. So H will be some reparameterization of the norm of P with respect to G. Okay? Where F will be a function of the following type. So well, F will essentially just be a bump function. Okay, so near 0 it will be almost flat, but still decreasing. Then it will decrease quite rapidly. It will take some linear slope, and then go to 0. So that's what F will look like. Okay. Well, it's well known that, of course, if I took the norm of P squared here, the Hamiltonian flow would be the geodesic flow, or the Hamiltonian version of the geodesic flow. And this is just a reparameterization of this. And so these are related by reparameterization. So the Hamiltonian vector field of H will be related to, I'll say, the kinetic energy Hamiltonian vector field in the following way. We just have we have one factor. I'll let you look at this. It's easy to verify, of course. So what do we know about the periodic orbits of H? Well, we know that they're just, they project to closed geodesics. Okay, so if X is a periodic orbit of H, well, so I didn't say, but it's clear that we choose this constant epsilon small enough so that the support of this function is inside of U. Is okay? And I also want to give a name to the maximum value of this function. I'll call it big A. So X is a periodic orbit of H. So in other words, we can recognize X lies inside of U, so we can recognize, let's see, X of t as Q of t, P of t. And we know that Q of t is a closed geodesic of G. So Q of t is a closed geodesic. Okay? The period of X is a periodic orbit of H, and the period, is the period of Q is a closed geodesic. No, here I didn't say the correct word. So there's a normal neighborhood theorem for Lagrangian submanifolds. So there exists a neighborhood U of L, which can be identified with the neighborhood of the cotangent bundle, and I've been identifying it without saying so. It's okay. All right, so that doesn't tell us how to get rigidity. So here's the path to rigidity through considerations of such dynamical systems. So we really only have one meaningful assumption to start with. L is displaceable. And somehow this has to give us some usable information. And here is where the input from the study of Hofer's geometry comes in. This will be kind of a black box for now, but I'll try to fill this in later. So L is displaceable means that if we take this maximum to be sufficiently large, one can detect a non-constant periodic orbit of H. Okay? Only the non-constant orbits are of interest to us. They're the ones that, sorry, I should have. Of course, we only know they project to closed geodesics if they're non-constant. We have, of course, all these constant orbits here. So for A sufficiently large, there exists a non-constant periodic orbit of H, let's say X, and well, we know more about it. This black box tells us a lot of information about the nature of these periodic orbits. We know at least that it's Conley-Zender index, not defined in general. So if we pick a capping, we can pick a capping which will equal m plus 1. Okay? We can find it. The point is that we can find a very special non-constant periodic orbit. All right. So this is some information obtained in a non-trivial way, which I haven't described, but I will. And this can be translated into information about the Maslov class. In the following situation, we need to add an assumption. And this assumption is similar to Viterbell's assumption. So there exists a G with non-positive sectional curvature. Okay, so we only consider these dynamical systems for such G's. In that case, this index can be related to the Maslov index of what? Well, we need an element of pi, the relative homotopy group. Okay? Well, we have a projection of x to L, so that's a loop Q. It's contractible, so we can pick A capping. There exists A capping. And what we will find is that the value of the Maslov class of this loop, this cap loop, will be between 1 and n plus 1. With possibly another factor of s of 1. I will be more explicit about this in a second, but in this scheme, we can deal with non-orientable Lagrangians, which is not as trivial a generalization as you think. There's a kind of a rich class of examples of non-orientable Lagrangian submanifolds. In particular, in R4, the only surfaces which emit Lagrangian embeddings into R4 are tori and certain non-orientable surfaces. And those constructions are due to Giventhal. All right. Okay, so for the sake of time, I'll just mention it and not write it, but there is definitely another approach to attaining Maslov class rigidity, and this is a relatively new set of ideas due to Fukaya, which relates the study of holomorphic disks with boundary on a Lagrangian to the string topology of the underlying Lagrangian. And these give very strict restrictions on the Maslov class. Despite the fact that they are defined using Lagrangian disks, like the first method, they're more related to the second method. And one can recover them in the Hamiltonian setting, or one can translate them in the Hamiltonian setting using work of Peter Albers. But that's perhaps a story for another time. Definitely a story for another time. Okay. Okay. So the theorem I wanted to describe today is the following. Now I'll need to make some assumptions on my ambient symplectic manifold. So let's let L inside of symplectic manifold M omega be displaceable. Suppose the symplectic manifold is another phrase which has been used before here, symplectically aspherical. So let me remind you, that means that if you look at omega restricted to pi 2 of m, that's 0, and so is the first Chern class restricted to pi 2 of m. Okay, this is a restrictive assumption on the ambient symplectic manifold. So in this case, if L admits a metric with non-positive sectional curvature, then we get that the minimal Maslov number is between 1 and n plus 1 plus 1, possibly where the second plus 1 only can contribute if L is non-orientable. So here plus 1 in brackets equals 0 if L is orientable. Okay, so some remarks. This theorem covers Lagrangian tori, the relatively important case of Lagrangian tori which are non-monotone. So I should say that monotone symplectic manifolds, this is this is a relatively strict condition to place in a Lagrangian submanifold, but it's an extremely important notion. It arises in many cases. However, for rigidity results, one would like to move away from this class of Lagrangians, and this theorem does so. For the case of tori and other manifolds which admit metrics of non-positive sectional curvature. And again, we don't worry about orientability. All right. Okay, so before I start to describe how to prove such a result, let me just make the following simple observation. Here, because we're assuming that C1 vanishes on pi 2, it's possible to think of the Maslov class not as a map from pi to ML to Z, but from a map from, let's say, the kernel of I star to Z, where I star is the map induced in the fundamental groups by inclusion. I don't have to worry about the role played by spanning disks. It doesn't affect the computation under this assumption. Okay? So in other words, as need be, we will be able to just write the Maslov class of a loop in L, and I won't have to worry about spanning disks. Okay? All right. So let me describe the proof, or start to describe the proof. Okay, well, we'll start with these Hamiltonians again, except I'll give them one more precise feature. I'll just label this constant slope. So here, f prime equals c. In this region, okay, this will still be, of course, a. This will be epsilon. We won't need epsilon once we assume it's small enough. And now we see that, so what can we tell about the length of these closed geodesics? It's easy to compute. So if we want to compute the length of a closed geodesic corresponding to a periodic orbit of H, it takes perhaps a second and a half to compute it as follows. Okay, so it only depends on what level set, the slope of the level set that it occurs on. These are autonomous Hamiltonians. So if C, if this constant slope is not in the length spectrum of G, then we can find our orbits in one of two spaces. They don't exist here, right? Any orbit, any periodic orbit here would correspond to a closed geodesic of length c, which is outside of our length spectrum. So then x occurs in one of two regions, G or B. So this would be G, and this region where the slope changes from C to 0 would be B. Okay? All right. So now, sorry, f only has to be a positive. Sorry, why not? Say. Oh, sorry, this slope is meant to be quite small as possible. So there will be no non-constant orbits there. That's okay? All right. Following this line of reasoning, well, eventually we will have to detect a nice periodic orbit of these Hamiltonian flows and then relate its Conley-Zender index to the value of the Maslov class on the projection. So I want to talk about this index relation first. Okay, so call this the index master equation. And this is due to Duistermaat, and part of it's due, half of it is due to Duistermaat, and half of it is due to Viterbal. Okay, so here is it's a little messy, but then we will simplify it with our assumptions simplify this equation a lot. So let's let x equal qp, so these are functions of time, be a non-constant orbit of h. All right, so here I will fudge one subtle issue a bit. This is an autonomous Hamiltonian, and in terms of floor theory, its closed orbits are degenerate. I want to consider non-degenerate orbits. So one can, in a careful but standard way, perturb this picture and talk about non-degenerate orbits. So from now on, I will be really considering perturbations of this orbit x, which are non-degenerate. Okay, I don't want to give them different notation. It's a little messy, and I want to avoid this issue a bit. But if it confuses you, please say so. All right, then we have the following equation for the value of the Maslov class on Q. Okay, so Q is the projection of x. We're in this situation where we can define the Maslov class on loops in L, which are contractible in M. And we get the following identity. It's equal to the Conley-Zender index of x minus the Morse index of Q. Q is a closed geodesic. It has a natural Morse index. There's Morse theory, of course, for closed geodesics. Minus some number d, which I will tell you about in a second. And then plus 1, which this plus 1 in round brackets, as usual, corresponds to matters of orientability. And then we have another plus 1 in square brackets. Okay, so let me describe the mystery terms here. Okay, well, let's get rid of the easy ones first. The plus 1 equals 0 if x is in G, and, well, plus 1 if x is in B. Okay, so it's the difference between being convex and concave causes us possibly a plus 1. All right. Now, well, this plus 1 is the same one as before. It vanishes if L is orientable. Okay, so plus 1 equals 0 if L is orientable. The Conley-Zender index has been used enough that I won't worry about defining it. It's a natural object in the study of Hamiltonian dynamical systems. And the Morse index is, of course, classical. So all I have to do is tell you what D is. All right, so D stems from the fact that I've perturbed things. Okay? Well, we have a metric with non-positive sectional curvature. The closed geodesics come in non-degenerate critical submanifolds. And D, well, we can assume that we're in that case. And then D is the maximum dimension of a critical submanifold. Critical submanifold of what? Of the energy functional, which is the Morse function for geodesics, from which we're deriving the Morse index already. So it's the maximum dimension of a critical submanifold of non-constant geodesics. Yes. Not clearly necessary, but let me just assume that for a second. Okay, so what do we know about D in the case of non-positive sectional curvature? Well, we know some typical examples. If L is the torus and G is flat, or if, in any case, if G is flat, then D is equal to N. We have the critical GOD6 of a torus arise in the same dimension family. And if G is hyperbolic, then this number D is equal to, let me go back just a second here. Let's let D little g be this number. So this would be D little g. Okay, so this is a maximum dimension. And the number D which appears here, what we will know about it is that, so this is what happens under perturbation. We have a critical submanifold of this dimension, let's say, but that's the worst case scenario. When we perturb it, we get critical points whose indices then shift from the Morse index of that critical submanifold, and it can, we can add 0, or we can add all the way up to the dimension of the submanifold. This is the price of perturbing a critical submanifold. That's all this number D is capturing. So the number D, which appears here, is between 0 and dg. Okay, which appears in this formula. That's what we can say about it. All right. Okay, I should say that we have these examples, these reasonably interesting examples of the torus where dg is equal to n, and the case of hyperbolic manifolds where dg is equal to 1. Of course, the GOD6 are isolated in that case. In general, this is the worst case scenario for dg, for non-positive sectional curvature. So always dg is less than or equal to n. For non-positive sectional curvature, you just have to consider the kernel of the energy functional. You can see that it's generated by constant Jacobi fields in this case, so you just need an initial condition. So n dimensions. Okay. All right. So now we notice that now we can use this formula to see exactly what we need to know about the Conley-Zender index of X to get useful information about the value of the Maslov class. Okay?
So hyperbolic is constant curvature?
Negative sectional curvature. Strictly negative sectional curvature. I don't want to make that assumption. Just negative. Well, I guess it's just terminology, but okay. So note that if X is in G, so G stands, of course, for good area, and B for bad area, and the Conley-Zender index of X is equal to n plus 1, then this formula tells us that the Maslov, the image of the Maslov class on Q is equal to n plus 1. What do we know about the Morse index for non-positive sectional curvature? It is, of course, 0. Okay, so this term vanishes. We get minus d. And then we can have this plus 1. Okay, and all other terms, well, the square bracket plus 1 vanishes because we're in G. All right, and so finally we get that this is taking values in, well, if D can be at most n, the smallest this number can be is 1. And if D is 0, the largest this number can be is n plus 1, and possibly another plus 1. Okay, so in other words, that is the object of interest. A non-constant periodic orbit of such a Hamiltonian with Conley-Zender index equal to n plus 1. Okay? Now, the n plus 1 is a bit off-putting for the following reason. One would like to detect this periodic orbit using the Floor homology of this function, this Hamiltonian. And, well, the basic fact about the Floor homology is that up to a shift, it's equal to the singular homology. Okay? So we know that it's non-zero for a choice of normalizations between n, minus n, and n. Okay? So this has Conley's-Zender index n. So in that sense, it's not obviously visible via homology. It's not homologically visible, if that's a reasonable phrase. So we have to find it in some other way. We can't, if this is meaningful, we can't find it in terms of the usual action selectors. So we need something new. So I want to finish by describing this something new. Okay. So as I mentioned, we will consider the Floor homology of H. I think as Otto mentioned, this is, or perhaps someone else, I apologize. This is the Morse theory for an action functional on the space of loops. So my convention will be the integral of H to T over the symplectic area of X. So we will consider this. I said it's not homologically visible, which suggests that you have to, well, not work with a full homology. You need the finer structure of Floor homology. And so we will start with the following simple specialization. We will consider the Floor homology restricted to action values less than b. Okay? So here b will be a constant greater than a, which I will just remind you is the maximum of our function h. Okay? And this is just, well, the Floor homology is the homology of a complex. Every critical point has an action, and the boundary map decreases actions. So if you pick some action level b, and you just look at all periodic orbits with action less than b, the boundary map respects that set and descends to a boundary map. And so you can define a homology. This is no longer an invariant of the symplectic manifold, but still a useful object to consider. Okay. All right. So the point that this periodic orbit has to be involved in some phenomenon for us to detect it. So it turns out that for b greater than a, the following fact is true. There exists two natural ways to define a fundamental class, which is kind of a silly thing to say. You think a fundamental class would be unique. Anyway, there's two natural ways to define a fundamental class in this object, which is not an invariant, so it's kind of a strange thing to say already. And they are not equal. And this orbit detects, in some way, the size of the difference. Okay, so let me describe that. All right, so I'll describe each of these two fundamental classes in two ways, just with a picture, where of course there are no rules, and one in terms of homology, so that I don't have to talk about perturbations. So the first one is as follows. We have this kind of picture of our Hamiltonian. H, well, I can think of this as F or H. And I wanted to find something like a fundamental class. So if this was the full Floor homology, there would be one way to do this, or one answer anyway. And one way to get it would be to consider a small Morse function. So instead of this being the real line, let me picture this as m. Okay? So this would correspond to the neighborhood U, where this is supported. So let's consider just a small Morse function on on M. I will draw it like this for the following reasons. So this is a Morse function f. And just to keep track of the fact that it's small, I will say epsilon times f. Or maybe delta times f, because I've used epsilon. OK? So one can consider the floor homology of this Morse function. Okay? It's, of course, isomorphic to the homology of the manifold. And there's an isomorphism between this homology and the full homology. Now, let's suppose that this has a unique maximum at a point Q. Okay. So in the floor homology, Q represents a non-trivial class, the fundamental class. Okay? And when I compare the floor homology of this small Morse function with the floor homology of my original function, the image of this will be something which is reasonable to call a fundamental class. So let me describe the picture in terms of maps and floor homology. So let's start with the part of the picture I just described. We have the floor homology of H, and we have the floor homology of our small Morse function. And there is a natural map defined in floor homology, which is an isomorphism. So let me call that map sigma with this accent, and this is an isomorphism. Okay? This can be identified with the homology of the manifold. This is isomorphic to the homology of the manifold. You have to shift degrees. I won't write that down. But of course, we started with not the full homology, but the restricted floor homology. Okay. So there's a natural map between the restricted floor homology and the full homology induced by inclusion. So this was generated by all periodic points, periodic orbits with action less than b. These are, of course, included in the set of all periodic orbits, and this inclusion induces a chain map in homology. Okay, so this is a natural map. We don't know anything about this map in general. And I should put a B here, of course. It's okay? All right. Now, of course, for the same map exists for the restricted Morse homology, restricted floor homology of this Morse function. We have IB. And in this case, it's not too hard to convince yourself that if delta is sufficiently small, this is an isomorphism. Okay? So this is an isomorphism if delta is sufficiently small. Okay? Moreover, there is a map this way. Let me call it sigma b. And if, again, if delta is sufficiently small, then we can assume that this, or we can prove that this diagram commutes. Okay? What's that? Why? Which part is concerning you? Well, actually, why is technically the, if I choose, so of course, these maps are defined in terms of homotopies between this function and this function. If I choose that homotopy correctly, on the chain level, this map will equal this map. Okay, it won't go outside of the range B. Okay, so these maps will actually be equal on the chain level. Okay, it's not, I assure you it's not a deep fact. Okay. And so in terms of this diagram, one could define a fundamental class for this homology in the following way. We just take the fundamental class here. We take its inverse image under this isomorphism. And then we map it over here. Okay? Okay, so I'll refer to this class as the class of alpha. Okay. So there is a second way to define a fundamental class. Let me just do it very briefly. All right. So instead of starting with the Morse function here, there's nothing. So there are many special features of this function. One of them is that this is a name. This is the definition of the fundamental class, and this is how I'm going to refer to it instead of writing these symbols. Is that okay? All right. So one special feature of this function is that it has a fixed maximum. Okay. So instead of looking at delta f here, let's just move it so that its maximum is right here. So that would be delta f plus a. Still a Morse function. I've just shifted its graph. Okay. Well, we can still consider its floor homology. Its floor homology is still equal to the homology of M, and I can still consider all these maps. Okay, so in this way I get a different, so let me draw the diagram here. So we have, again, this homology. We have HFB delta F plus A. And here I'm going to draw the map with the accent in the other direction. And you'll ask me why this is well defined. And I'll tell you it's because you can use a monotone homotopy. Is this okay? All right. And then this is, of course, injects into, or sorry, there's a map into the full floor homology. And we can define a second fundamental class. This is isomorphic to the homology of the manifold. And we can take M, I, B inverse, and then sigma down B. And we'll call that beta. Okay, so if we're talking about the full floor homology, these two classes are, if you look at the image of these two classes in the full floor homology, so here they have the same image. In other words, for B sufficiently large, one can show that alpha, the class alpha is equal to beta. However, for B approximately, well, greater than A, but approximately equal to A, in fact, they're different. I'm sorry, I don't have time to show that, but the basic reason is that the class here, so if you look at the image of the maximum here, this class is represented by something whose action is A. This class alpha is represented by a chain whose action is strictly less than A. So they cannot be equal in the restricted floor homology if B is close to A. There's nothing to hit them. There's nothing to hit the difference. Okay, so perhaps a subtle point. But one can then consider the following quantity. Gamma of H is the infimum over B greater than or equal to 0, such that alpha equals beta in HF B of H. Okay, so it's if you like, the minimum B at which they're always equal. They're not equal for small b, they're equal for large b. Okay. Well, this is all right. I'll end up quickly. This is an action selector. and it is it realizes the difference between two floor homology classes in degree n. So it's really seeing a boundary operator from something larger. Okay, so the fact here is that gamma h is realized by an x with Conley's under index equal to n plus 1. There's one missing feature. We need x to be in this region G. Well, I said that this is an action selector. It has the same continuity properties as an action selector. And exploiting these, you can show that for a large enough, or for some a large enough, this x has to be in G. So we found the object that we're interested in. Just as a point, I said that this is an action selector. This is true, but I've only recently realized it's not the best way to look at this object. The best object, perhaps the more interesting object, is the difference between alpha h and minus a. This turns out to be related to the boundary depth of Usher, recently introduced by Usher, and this is maybe a story also for a different time. Okay, I'll stop here.
Other questions?
Can you give an example of some Lagrangian that is still precludes in some manifold which is not expect maybe like
Yes, well, one kind of inherits these examples. There are examples, I think due to Polterovich, of so-called higher dimensional Klein bottles. So this doesn't include the Klein bottle. It includes analogs of the Klein bottle in spaces of dimension at least 6. If these existed as displaceable Lagrangian submanifolds, it would imply the existence, so you can, using these, a normal neighborhood of these Klein bottles, you can embed a Lagrangian torus. And if such a Klein bottle exists, you could embed a Lagrangian torus with a Maslov index higher than n plus 1, is what I'll say. So these cannot exist and be displaceable. So that there are examples where you can preclude, or I mean, you can put it the other way and show that these things always have to these Klein bottles would always have to intersect themselves. They couldn't be displaced. I got rid of that term involving the Morse index and the index relation.
Any other question? So let's thank Ellie again.